So we have discussed the basic working principle of transformer, okay, and the ideal transformer, okay. But now we are going to move towards the practical transformer, okay. So the very first discussion here is the no load current. So we have seen in an ideal transformer that no current will be taken by the primary winding from the source, right, if the secondary current is not flowing, okay, but that is not the case with the actual transformer, okay. So there is going to be some no load current, or it is also called as excitation current. Now the magnitude of this current, this is going to be about 5% of the full load current or the rated current. So this no load current, this is going to have two components. First one is the magnetization current, okay, and the second one is the core loss current. So the magnetization current, this is drawn by the transformer to produce the flux, to set up the flux in the magnetic core, okay. And the core loss current, this accounts for the core losses. We have hysteresis and eddy current losses, right. So the current required for these losses, that is the core loss current required for hysteresis and eddy current losses. So we will discuss each of this one by one. First we will discuss the magnetization current. So if you consider the magnetic core, we saw that the primary winding itself will have an induced voltage, right. So this is the primary winding. To this we have a voltage source connected, okay, and to this we have the secondary winding. Currently we are talking about no load, so the secondary current is 0. Now what is happening when you give a voltage, say V1, okay, then what will be the induced voltage that is produced here? This is going to be like this, right, E1 with the given polarity. Now let us say the flux that is produced is phi, right, it will be in the clockwise direction. So here we are taking the current, the sense of winding, everything we know. So we know the flux direction and the induced EMF polarity, okay. So now we can write E1 is equal to N1, if this is number of turns N1, d phi by dt, okay. So remember, we have not taken the negative sign here because the polarity we have already taken, okay. We have seen all the directions, so we have already set the right polarity. So that's why E1 is equal to plus N1 d phi by dt. Remember that, okay. Now what is going to happen? E1 is what? It is nothing but equal to this voltage, the given voltage, right. So this is going to be V1 is equal to N1 d phi by dt. So from here what will you get? Phi. This is going to be 1 by N1 integral V1 dt. Now the source voltage, it is an AC source. So if you are taking it as Vm some cos omega t, okay, then what will you get? Phi. This you are going to get as 1 by N1 integral Vm cos omega t dt, okay. So what you are going to get? Vm by omega N1 sin omega t. So here we see that the flux is a sinusoidal quantity, okay. Now there will be some current that is required to set up this flux, right. From the magnetic circuit equation, MMF is equal to the flux into reluctance, right. And what is MMF? MMF is nothing but N into I, okay. Now this current that is required to set up the flux, this is the magnetizing current, magnetization current IM. Now the question is, what is the nature of this magnetization current? Whether it is sinusoidal, it is a constant, or it is having some harmonics. So you will get information of this from the BH curve, right? This is the BH curve, right? B or phi, here you have H or MMF, okay? So now what we are going to do, we are going to draw the flux with respect to time here. So flux is a sinusoidal quantity, right? So you can draw one cycle like this, okay? Now what you have to do is, you have to project each of the points onto the BH curve. Let's say we are taking some point on the flux line, okay? Now this point we have to project onto this, okay? And this point will be corresponding to some current, okay? And that current we will draw on a separate graph, okay? So this is the flux value. So this is the point of intersection, okay? That means for this value of flux, this will be the current. So what we do, we project onto another axis which will become our current cycle, current variation, okay? This is I with respect to t, okay? So we just have to put it here, okay? Now this is the value of current. Now at which time? At this time. See, if this point is taken at T1, here also at T1 the current is going to be this value, okay? Similarly, if you are going to project all of these lines, what is going to happen? If it was a linear curve, if BH curve was linear, what will happen? For a sinusoidal flux, you are going to get a sinusoidal current. That's what is linearity, right? But now there is a non-linearity coming into picture. Initially there is linearity, but then again non-linearity will come. So what will happen in non-linearity? For a small change in the flux, there is going to be a huge change in the current. So you can draw, this is one point that we have drawn here, let us say, okay? And we will take a point here. Now what is the difference in flux here? This is going to be a very small quantity, okay? But this, if you project onto the BH curve, you are going to get somewhere like this, okay? Now if you project it onto the current, then you can see that the difference, it is going to be large, okay? See the difference between this and this, okay? So the resulting current, this is not going to be a sinusoidal value, okay? This is going to be looking something like this, okay? So you can write down a few points here. The current required to set up sinusoidal flux in the core is called the magnetization current, IM. So this is IM here. And due to the non-linearity of BH curve. So here if you are wondering what happened to the BH loop, okay, so that we are not considering here. We will be considering that in the core loss component of current, okay. So due to non-linearity of BH curve, small change in flux will result in large changes in current, in magnetizing current, okay. So this results in a peaky nature of magnetizing current. So this peaky nature basically indicates that there is a third harmonic current, okay. So this peaky nature indicates presence of third harmonic. So what is harmonic? So we saw this flux, this is having a frequency omega, okay. So this is called as the fundamental frequency. Now when you talk about harmonics, the second, third or fourth harmonic, what is going to happen? We are talking about the components which are having a frequency which is twice or thrice the fundamental component. So for example, if you take, this is a pure sinusoidal wave. Now let us say this frequency is omega, okay. Now what will be the third harmonic this is going to have a frequency of 3 omega. Third harmonic is going to have a frequency of 3 times of the fundamental component. So what is going to happen? By the time this completes one cycle, the third harmonic component is going to complete 3 cycles. Okay, so it is going to be something like this. Okay, so you can see this is one cycle, second cycle and third cycle. So this peaky nature indicates presence of third harmonic. So how is that? Why is that the case? So this is one kind of harmonic that I have drawn. Now another way it can be present, the third harmonic can be present, is if this is the main sinusoidal, main fundamental frequency, then the third frequency, see here I have drawn from starting from like this, normal sine wave. But here if I draw in this manner, so what is going to happen here? If you add this fundamental and the third harmonic component, you are going to get a peaky resultant. So this is going to be something like this. Okay, so you can see here during this part, this is negative value. Okay, so this is going to be a little lesser than the actual fundamental component, while when this starts, the peak is also going to start. Okay, so that is why, since the magnetizing current, this is how we got the magnetizing current, right? So that is why we say that the magnetization current, it is going to have a third harmonic component. Now one more important thing that you have to observe about the magnetizing current. So you can see that the flux, this is going to be lagging the voltage by 90 degrees. See, V1 is cos omega t, right? Cos will lead the sine by 90 degrees. So flux is going to lag the applied voltage by 90 degrees, and the magnetizing current, this is going to be in phase with the flux, right? So the magnetizing current IM is going to lag the applied voltage by 90 degrees. Okay. Next we will go ahead with the core loss current. So as already discussed, this is going to account for the hysteresis and eddy current losses. Okay. Now these losses, they derive active power, real power from the source. Okay. So real power means what will happen? This core loss component, this we can write as IC, this is going to be in phase with the applied voltage. Okay. So IC is in phase with applied voltage. So this is in contrast to the magnetization current that was lagging the applied voltage by 90 degrees. And one more important thing is the core loss component, this is also a non-linear value. Okay. Now we will try to draw the phasor diagram of the transformer at no load. So if you draw the magnetic core here, first we will write down all of the parameters that we need to represent in the phasor diagram. So this is the primary winding, and the voltage that is given to this we will take as V1. Okay, and what will be the induced EMF? Polarity is going to be this, and you will take it as E1. Okay, and on the other side, the secondary winding, this induced EMF is going to be E2. We will take it as E2. So here see that we are taking the small letters. Small letters is what? They represent the instantaneous values, right? For example, if this is V1, V1 of t is equal to Vm cos omega t, let us say. Okay. Now this is going to be a small letter. It is the instantaneous value. Now how will you write the phasor? Phasor is going to be capital V1. We can use the bar as well. This is equal to Vm angle 0 degrees. This is the correct representation. Okay. So now we will start drawing the phasor diagram starting from the supply voltage V1. Okay. So V1 bar, since we have taken it to be having a phase 0 degrees, we will take it as the reference. So this is going to be V1 bar. Okay. Now this is equal to the induced EMF E1 bar, right? V1 bar is equal to E1 bar. Now what about this voltage E2, the induced EMF on the secondary winding? This is also going to be in phase with this, okay? So you can take, depending, it will depend on the turns ratio, the magnitude, but I will just take to be somewhere here, okay? So this is E2 bar, okay? Next, because of this, let us say a flux phi is going to be produced. Now we already saw the flux is going to lag the supply voltage by 90 degrees, right? So here we can draw the flux like this, okay? This is the flux. Now what is left? We have to draw the excitation current. So we can either represent as IE or I naught. In different textbook, different notations are used. Now we know that this excitation current, this has two components. One is the magnetizing component and other is the core loss component, okay? Now the magnetizing current, this is going to be in phase with the flux, we already discussed, right? So here we can draw, this is E2 and here we can draw the current, magnetizing current IM. So here we have to represent only the phasor values, right? So IM bar, okay? Now what about the core loss component? This is going to be in phase with the supply voltage, okay? So here you can write IC bar, okay? So the core loss component is going to be much less in magnitude as compared to the magnetizing current. Now what will be the excitation current or the no load current? Is going to be the phasor sum of IC bar and IM bar, okay? So if you add these two, this is how you add, right, the phasors. Then you are going to get the no load current or the excitation current, I naught bar, okay? Now what is this angle between I naught bar and V1 bar? This is going to be the power factor angle, right? So we will take this as theta naught, okay? And this angle, the angle between IM bar and I naught bar, this is going to be the alpha naught and this is called as the hysteresis angle, okay? Alpha naught is the hysteresis angle and theta naught is the power factor angle of no load current, okay?